All right, so today we're going to start 2.4, which is derivative. Finally, we got to derivative. And when you think derivative, the first thing that should come to mind is rate of change. And you've heard that before. Rate of change, rate of change. Where have you heard rate of change before? You heard it when we were talking about slope when you did algebra. And that's really where derivatives begin. It begins with slope, right? And all of you have done slope before. Now, slope is average rate of change, how things change over time from here to here. Derivative is not from here to here. Derivative is instantaneous rate of change. It's the rate of change right now, not 1 hour to another hour. It's right now, this very second. How is it changing? And everything is about changing. And you're like, why is it important to find out derivative? What is derivative? Well, there's two kind of definitions. Finding the equation of the line to the function of a particular point. That's more of like in calculus 1, you go into the little theory, how can it be used? We're going to be focusing on B, finding the instantaneous velocity or rate of change of something. It could be an object, it could be cost, it could be revenue, it could be profit. If you can figure out how stuff is changing, you're learning about it, you can react to it, you can make money off of it, all that wonderful stuff. You just have to figure out how things are changing, So the whole thing is going to start with slope. And as soon as I say slope, all of you remember m equals y2 minus y1 over x2 minus x1. So when you have a point, x1, y1, and x2, y2, if you want to find the rate of change, you do slope. All of you remember that, right? It's the change in y over the change in x. So a real quick example, there's actually a little typo here we'll fix. Is an example of average rate of change is if you started at 10 a.m. and you ended at 1 p.m., your car started at 12,400 miles and it ended at 12,580 miles. What was the average rate? Well, you would take the change in the y's. So if you did 12,580 minus 12,400, you would get the change in y, which is 180 miles. And then this is where they made a little mistake. From 10 a.m. to 1 a.m. is actually how many hours? 3 hours. 3 hours. And if you divided that, you would find out, yes, you've gone 180 miles. Yes, you've gone for 3 hours, but the average rate of change is 60 miles per hour. Now, maybe you went a little faster the first hour, maybe you went a little slower the second hour, but on average rate of change, that's what happened. Are we okay? Now, how do I get you from this formula slope that you're very comfortable with to get to derivative? Well, we're going to do that in a little bit of a process. So if I teach you slope is y2 minus y1 over x2 minus x1, all of you are totally cool with that. You remember that. Everything's okay. Then I tell you, what if instead of doing that, I give you another formula? F of b minus f of a over b minus a. And you're like, okay, that looks a little different. But it also kind of looks the same. So this is saying instead of x1 and y1, this is a and f of a and the result of a. And this would be b and f of b. So yes, it looks a little weird, but if you look at it, you're like, okay, it's the same thing. So to jump from slope formula to this other form of slope formula, looking at it instead of x1, y1, a, f of a, x2, y2, b, f of b, you can kind of see that they're the same. So hopefully going from that one to that one is not too bad. But ultimately what I want to get to, it's still slope, it's still the same thing, but I want to get to this formula, f of a plus h minus f of a all over h. Now I know that looks weird. Now we're saying, all right, hold on. That does look a little weird. That does look a little weird now, but all three are the same. All three are the same. All three are the same. And I'm going to show you that they're the same. We're going to prove that they're the same today. But what's the difference? Notice that the second one goes from f of a to f of b. And this one goes from f of a to f of a plus h. So what is h? H is b minus a. Kind of like how many hours have gone by. Well, okay, b minus a is h. Okay, we're good there. What's the difference? The second one is saying, okay, we're going from 5 to, let's say, 8. And so we do actually 8 minus 5. This one's saying we're going to go from 5 to 3 hours later. Well, isn't 3 hours later just 8? Aren't they the same thing? They are. Okay, so I know it looks a little weird, but basically we're going to go from number 1 to number 2 to number 3, but the bottom line is they're all the same. They're all the same. They're all the same. Okay, but our goal is to get to this formula. This is your part of your definition of what a derivative is. Definition of what a derivative is. And right now you should be thinking derivative is slope, it's rate of change. And if you got that, you're doing great. Okay, so here's our first problem. A company manufactures plastic planter boxes and the revenue is given by this. So X is number of planter boxes. You can only produce between 0 and 1,000 of those boxes. That's the capacity you have. And revenue is 20x minus 0.02x squared. And I want to know the average rate of change from 100 planter to 400 planters. And we're going to do this using all three formulas. Okay. Now, in order to do this, before we can even get started, I need 2 points. I need 2 points. So if we look at it the old way, x1, y1, x2, and let's say y2. Okay, well, I know that the first one starts at 100, comma, and the second one starts at 400. Now, what I don't have is the y. What I don't have is the y. So if you have the revenue and you know how many boxes, planter boxes, can I find the revenue and can I find the revenue? What do you have to do? Plug it in. So again, using our calculator, we go to y equals. I'm going to make sure my plots are off and everything's off so I don't have any weird things going on. I'm going to put in y1, the revenue. The revenue was 20x minus 0.02x squared. And again, that's my revenue. That's my revenue. They gave me the X values, 100, 400. So I'm going to find out how much revenue I make from 100 and how much revenue I make from 400. So I go to the table, delete whatever I got in there. And we're going to put in 100 and we're going to put in 400. So I get 1,800 and 4,800. So I now have my 2 points. 100 planters gives me a revenue of 1,800. 400 planters gives me a revenue of 4,800. Now, we're going to do this problem basically 3 ways, but we should get the same answer all 3 ways. The first way is using the formula we know, y2 minus y1 over x2 minus x1. Then we're going to use the second formula. The second formula is f of b minus f of a over b minus a. And then we're going to do it the third way using the formula we ultimately want to get to, which is f of a plus h minus f of a all over h. But the main goal right now is to understand that all three are sloped. All three are the same, and all three are going to give you the same answer. So what I want you to do is just the first one. Just do the first one right now. So if we fill this in, doing the first one, y2 is 4,800, minus y1 is 1,800, all over x2, 400, over x1, which is 100. That's going to give us 3,000 over 30, which gives us 10 over 1. Okay? Now, before we move on, let's talk about what we just found. What we just found is the change in y. So the 10 is talking about revenue. The 1 is talking about the planners, the box planners, right? So if I wanted to explain this in a sentence, I could write the average rate of change from 100 planters to 400 planters is. Now, notice, is this positive or negative 10? 10 over 1. What did we get? Positive 10. So that means it's increasing $10 per planter. So the average rate of change, and I'm just going to throw in their revenue, just to kind of set it up, from 100 planters to 400 planters is increasing $10 per planter. $10 per planter. We're learning how the planter is changing. The revenue is changing. Every one planter you get, we're getting $10 more in revenue. And just to be careful, it's 3,000 over 300. Thank you for that. 3,000 over 300, which gives you 10 over 1. 10 over 1. Thank you for catching it. Now we're going to do the second one, but please understand it's the same stuff. Same stuff. Now instead of x1, y1, x2, y2, we'll call the first one a, f of a, b, and f of b. It's basically the same thing, but instead of x, y, a, f of a. And then the other point is b, f of b. But it's basically the same thing. So f of b, b is 400, minus f of a is 100, over 400 minus 100. Now, f of 400 means what happens when you plug in 400? If you plug in 400, you get 4,800. Minus what happens when you plug in 100? The result of 100 is 1,800. Over 400 minus 100, you get 3,000 over 300. You still get 10 over 1. Okay, so take a minute and make sure that you understand the first and the second are the same. They're the same, they're the same, they're the... Now the new one. The difference between the second and the third one is this h. H is b minus a, b minus a, b minus a. So b in this case is 400, minus a in this case is 100. Therefore, h is 300. And if you noticed, on the bottom of all of these, it always ends up being 300. It's the distance between the two. The distance between the two. And if you look at all three of them, They've all been the distance between the two, which is 300. Now, if we follow to the letter, this is f of a, which is 100, plus h, which is 300, minus f of a, which is 100. And then again, I'm going to show every single step. 100 plus 300 is 400. So you have f of 400 minus f of 100 over 300. As you saw in the previous example, f of 400 is 4,800 minus f of 100 is 1,800 over 300. You get 3,000 over 300, which again gives you 10 over 1. All three are the same thing. The difference of all of these are the first one is what you're used to, x1, y1, x2, y2. But basically, we're going from 100 to 400. The second one is very similar, going from 100 to 400. The third one looks weird. Instead of going from 100 to 400, they're now saying this thing h. So instead of going from 100 to 400, we're going from 100 to 300 later. 100 to 300 later. But guess what? What is 300 later? It's still 400. It's still 400. It's still 400. Okay? It's just instead of going from 100 to 400, you're going from 100 to 300 later, which is still 400. So take a minute, look at all three. The goal is to start using the last one and understand that it's all slope. So now we're going to do another one. We're going to skip a little bit, skip a little bit, skip a little bit. And we're going to do this one, which is talking about velocity. Velocity is rate of change, right? So a small steel ball is dropped from a tower. I don't recommend that you do that, but let's say you saw somebody do that. And y is in feet, x is in seconds. So input is x in seconds. Output is y in feet. And bottom line, what is happening? You're dropping a ball from the top of a tower. So on the next page, we have a nice little picture of this going on. That's the Leaning Tower of Pisa. It's basically in the middle of nowhere. If you ever want to go visit it, it's cool, but it's the only thing around. Okay, it's not too far from Siena. But we're dropping the ball down is what's happening. And notice that as every second goes by, the ball is now further and further down. Okay? Now, the equation that models that is right here. 16x squared. 16x squared. I want the average velocity from 2 seconds to 3 seconds. So your job is you're given 2 points. 2 comma something, you got to find out the other one. 3 comma something, find out the other one. And then you're going to find all 3 ways. So y2 minus y1 over x2 minus x1, using that formula. F of b minus f of a over b minus a, using that formula. And the last one, f of a plus h minus f of a over h. You should get the same answer all 3 ways, and try to write it in a sentence if you can. But give all 3 a try, and we now have a new equation, 16x squared. So we have a new equation, 16x squared. So we're going to go to our calculator. We're going to go to y equals. We're going to change it to 16x squared. We're going to go to the table, second graph, and we're going to plug in 2 and 3. So you have to have these 2 points before you can do anything. So 2 comma 64 and 3 comma 144. So 264 and 3 144. Now, I'm just going to do the first one. I'm not going to do the other 2. Just going to do the first one to see how you're doing. So the first one is, again, if we label this x1, y1, x2, y2, nobody should have any problem finding slope or the first one because we've been reviewing it in this class, and also all of you had some sort of algebra. So that's 144 minus 64 over 3 minus 2. That should give you 80 over 1. So you now know the other two, you should get 80 over 1. And I'm not going to write it, but once you all of them get 80 over 1, try to write it in a sentence. Try to write it in a sentence. So if we're talking about f of A, f of B, this would be this would be A with f of A. This would be B with f of B, right? F of A is a result of A. F of B is a result of B, all functions. So if I fill in everything, this will be f of B, B is 3, minus f of A is 2, over 3 minus 2. F of 3 means the result of 3, which is 144. Minus f of 2, the result of 2 is 64, over 3 minus 2, which also gives you 80 over 1. Good so far? 80 over 1, 80 over 1. Now, the second one uses h. H is b minus a, the distance between them. 3 minus 2, how much time has gone by? 1 second. H is 1. It's how much time has gone by in this case. Only 1 second have gone by. And if you look at all three of them, they're going to have 1 on the bottom by the end. So h is 1. This is f of 2 plus 1 minus f of 2. Now again, this looks a little weird because the perspective is it isn't going from 2 to 3. It's going from 2 to a second later. But what is a second later? It's 3. It's the same thing. F of 3 minus f of 2 over 1. F of 3 is 144 minus f of 2 is 64 over 1. You still get 80 over 1. 80 over 1, 80 over 1, 80 over 1. And if I wrote this as a sentence, remember what we're doing is something called average change. The average change from 2 seconds to 3 seconds is increasing 80 what? Feet per second. The average rate of change from 2 seconds to 3 seconds is 80 feet per second. Again, that's not exactly what's happening. That's happening on average, right? On average, 80 feet per second. So now we can start using this last equation, which is what we need, and understanding it's just slope. Okay, so as we move on here, we're going to start getting into instantaneous rate of change. So instead of trying to find the rate of change from 2 to 3, I want to know the rate of change right now. The instantaneous rate of change. To find the rate of change, there's that slope formula. And notice part of the instantaneous rate of change, which is derivative, it has the limit. So notice that the formula has the limit in it. The formula has the limit in it, which means I had to explain to you what a limit is. I can't just put limit out of nowhere until I explain what a limit is. Okay, so notice that we have the slope formula and the limit as h approaches 0. All of this will start making sense, but this is the formula for instantaneous rate of change, which is derivative. So we keep going. There's some explanations. Again, remember, this isn't Calc 1. Ours is more to apply the calculus, because you'll see that it's the slope of the tangent line. They'll talk about all this kind of stuff. So when we have this derivative formula, how do we interpret a derivative? There's really 3 ways to interpret it. Our focus is going to be on 2 and 3. The first one says slope of the tangent line. It is the slope of the tangent line, right? That's not how we're going to use it. We're going to use it for number 2 and number 3. Instantaneous rate of change. How things are changing right now. and velocity, okay, which is the last example. So we're going to find out how things are changing right now. How is your speed changing? How is your revenue changing? How is your cost changing? How is your profit changing right now at this very moment? Okay, so having said all that, time to do the long way. So please keep in mind, we've been preparing for this. We have actually done this before, and now we're going to do it again. Okay, so what we're going to do is we're going to find the derivative of this function the long way. Now, why are we doing this? Let's kind of step away from the problem for 1 minute. Let's pretend this that I gave you is revenue. You plug in X, I can tell you revenue. Fantastic. All of us have been doing that for a very long time. I don't want the revenue function. I want the derivative of that function. What is that going to tell you? That's going to give you something called marginal revenue, or how the revenue is changing. So this formula right now is great if you want revenue. I don't want revenue. I want to know how the revenue is changing. So I'm going to take this function and I'm going to change it to a derivative function, how the revenue is changing. And how do you do that? You do that with your limit formula. The limit as h approaches 0 of f of. Now, instead of putting a, I'm going to put f of x, because that's the variable we're using. It could be any variable. They put a in the beginning to get you started, but it's just x. It's the variable. X plus h minus f of x all over h. Okay? Now, we're going to do this slowly, carefully, and I'm going to remind you that we've done this before. The only thing we're adding is this limit part. The only thing we're adding is this limit part. Okay? So I'm going to go slowly and carefully, but I'm going to warn you that I've already done this. I've already explained this. I've already done it, except for the limit part. Okay? So I'm going to use different colors. So this part right here says, go to your function, go to your function, go to your function, and where there's an x, what am I going to plug in? X plus h. Everywhere there's an x, I'm going to put x plus h. So nice and slowly, let me start this. It starts with limit as h approaches 0. We're going to keep writing that. And then I'm going to keep the red going. So in red, it says, go to this function. There's an x, I'm going to plug in x plus h. Everywhere there's an x, I'm going to plug in x plus h. And you're like, oh, we did that before. We totally did, a couple times. Okay? Then, again, I'm going to use different colors. The next part of the formula is a minus. And I'll even do this part in green, just to show you a little different. Minus f of x. What is f of x? F of x is what? The original function, which is negative 16 x squared plus 80x plus 6. And then we're going to divide all of this by what? H. So make sure you are comfortable with how I did all of that. And I'm going to give you a head start. The head start that I'm going to give you is, hopefully you know that x plus h squared means x plus h times x plus h. And if you work that out, that's going to be x squared plus hx plus hx plus h squared. You get x squared plus 2hx plus h squared. So I'm going to clean this up just a little bit for you. And I'm going to say that this becomes negative 16 times x squared plus 2hx plus h squared. I'll give you that little head start. But then I want you to do the rest. Be careful with the subtraction, as we talked about before. And I want you to do your best to clean this up as much as you can. Don't mess with the limit part. Don't mess with the limit part. Just do the algebra part to clean up that equation or that expression as much as you can. All right, so I'm going to go ahead and work out the algebra as you're working it out. Every single time, I'm going to keep putting limit as h approaches 0, because we'll deal with that later. That's the new part. But we're going to distribute the negative 16. So we get negative 16x squared minus 32hx minus 16h squared. Distribute the 80 plus 80x plus 80h plus 6. Then don't forget to distribute this minus the subtraction. So that's plus 16x squared minus 80x minus 6 all over h. And then this is where things start cleaning up a little bit. Again, we continue to write limit as h approaches 0. We're going to keep writing that. But then what ends up happening? What ends up happening is negative 16x squared plus 16x squared. 80x minus 80x. 6 minus 6. Which leaves us with, and again, this is all algebra. This leaves us with negative 32hx minus 16h squared plus 80, oops, keep writing that, plus 80h. All over h. Then a little bit more algebra. We're still writing limit as h approaches 0. We're going to factor out an h, which leaves you with negative 32x minus 16h plus 80 all over h. H over h is 1, and we get to this step here where h, limit as h approaches 0 of negative 32x minus 16h plus 80. Let's get to that point and make sure we're comfortable. Let's get to that point and make sure we're comfortable. Notice every single time I keep putting a limit as h approaches 0, 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 every single time. Why? Along the way, I can't plug in 0. It'd be undefined. Can't plug in 0, be undefined. Can't plug in 0, it would be undefined. Until you get to the last step. Excuse me. And since you've cleaned it up, simplified all that, now we can actually plug in 0 for h. So notice I stop writing limit as h approaches 0. I stop writing limit as h approaches 0 when you can actually plug in 0 for h. And then you end up with your final answer, negative 32x plus 80. And what is that? That is your derivative function. So notice, instead of just putting f of x, I put this little apostrophe. That's called prime. That's called a prime. That is called, this is the derivative function. Now, as you're getting that down in your notes, let's just step away for a second. The original function would be like revenue. How much money did we bring in today? This function, what we just found is how your revenue is changing. This is your derivative function. This is the derivative of revenue function. Are we okay? So if I plug into the original, that tells me total revenue. This one tells me, how is your revenue changing? Is your revenue going up? Is your revenue going down? Is your revenue staying the same? So hopefully we see what the purpose of this is. This is to tell me how my revenue is changing. Now, as you look at this, you're like, wow, that is a lot of work. That is a lot of algebra. And you're totally correct. You're totally correct. And guess what? We've done so many of these over and over and over again. We found a pattern. So instead of doing all of this work, we now can use that pattern because we know how to do it by hand. And that pattern is a really nice shortcut. So we started with negative 16x squared plus 80x plus 6. That's what we started with. Is everybody with me? And we did all of this work to get negative 32 plus 80. Now, I'm not going to do a good job because I'm going to do a good job later. I'm just going to show you what the shortcut is. Then I'll do a good job of explaining the shortcut in a minute. The shortcut is this. Instead of doing all of that work, do you see the exponent? Multiply it by the front. You take the exponent times the front, which gives you negative 32, and you always subtract 1. So you multiply and subtract 1. Multiply the exponent and subtract 1. It's always multiply and it's always subtract 1. Why? It's the pattern that develops. Now, this exponent is not there, but it's assumed to be a 1. What's 1 times 80? 80. And what's 1 minus 1? 0, so that's gone. And then the derivative of any number is 0. Why is the derivative of any number 0? Because there's no variable here. It's x to the 0. And what's 0 times 6? 0. So the derivative of any number is 0. Guess what? You just got the derivative without doing all that work. So the shortcut is multiply by the exponent, subtract 1. Multiply by the exponent, subtract 1. Would you like to do the shortcut? Or do you want to do all this work every single time? Shortcut, yeah. And again, you're complaining that you have this squared. What if it was to the 3rd? What if it was to the 5th? You'd be sitting here forever, right? So because we did it the long way, now we're going to do it the shortcut, okay? And then we'll focus on what it means.
Recording in progress.
Next section, we're going to talk about the shortcut. We're going to do the shortcut. We're going to do the shortcut over and over again when we get to the next section. But I just want to give you the basics of the shortcut. So here's the basics of the shortcut method. Again, we're going to practice this next section, and we're going to throw in a lot of weird stuff. You have a ton of homework that's going to help you with this, but I just want to teach you the basics, and hopefully it starts to click. Okay, so here's the basics. If you had a function x to the 8, and I wanted the derivative of that function, notice the notation. Without the prime, it's the original. With the prime, it's the derivative. So notice, how can we tell which is original, which is derivative? That little apostrophe. Are we okay? Now, you're like, oh, there's no number in front. There is a number in front. What's the number in front? It's a 1. So the shortcut method, I don't care if it's a number, what kind of number it is. It could be a fraction, could be a decimal, whatever it is. You take the exponent times the front. 8 times 1 is 8. And then you always subtract 1. 8 minus 1 is 7. Now, if you're like, why is that? Do it the long way. Plug in x plus h, raised to the 8, have it 8 times, minus the original, divided by h, work it all out, which will take you a very long time. You're going to get 8x to the 7. Right? Why do we know that? Because we did the long way so long, we found this pattern. Okay? So again, we're just going to keep doing it, and hopefully it starts clicking. So what if I had 3x to the 4? 3x to the 4. Okay. Well, to find the derivative, you take 4 times 3, which is 12, and you subtract 1. 4 minus 1 is 3. That's it. Multiply by the exponent, subtract 1. Multiply by the exponent, subtract 1. Multiply by the exponent, subtract 1. What if I had a negative? Oh, it doesn't matter. I don't care if it's a negative. I don't care if it's a decimal. I don't care if it's a fraction. It's still the same. To take the derivative, you take the exponent times the front. Negative 7 times negative 3 is positive 21. X, please be careful, and please, you need to know this. What's negative 7 minus 1? Negative 8, not negative 6. Use your calculator. You should know it. That's the kind of stuff that's going to throw us off. And again, we'll talk about cleaning up and all that later. I'm just kind of showing the basics. So what if I had, oh my gosh, he's going to do it. He's going to give us a fraction. Oh, does it matter? No, it's the same thing. Let's see how good we are. 1/2 times 4, 2. 1/2 minus 1, -1/2. If you stuttered a bit, maybe you need your calculator. Maybe you need to be careful. Okay, but again, the shortcut is multiply by the exponent, subtract 1. Multiply by the exponent, subtract 1. Now, one that tends to throw people off, and I want to talk about this one right now, is what if I just give you x? What's the derivative of x? Okay, now looking at it, you're like, I have no idea, because you don't see the number in front and you don't see the exponent, but it's there. What's the number in front? 1. What's the exponent? 1. So just put it there if you need it. Bless you. So if we take the derivative, what's 1 times 1? 1. And then what do you do to the exponent? Subtract 1. What's 1 minus 1? 0. X to the 0 means there are no more x's. So your answer is 1. Okay, let's extrapolate that a bit. What do I mean? What if I had f of x equals 5x? What would be the derivative? So there's a 1 here. 1 times 5 is 5. What's 1 minus 1? 0. Ooh, so wait a minute. Maybe we figured out another pattern. What's the derivative of anything x? The number in front, right? But again, know the y. If I had 2/3, another fraction, x, what's the derivative going to be? 2/3. Y. There's a 1 here. 1 times 2/3 is 2/3. 1 minus 1 is 0. So you find a little shortcut. Okay, that's good. What's the derivative? Pick a number. 18. What's the derivative of 18? Take a guess. 0. Why? Why is the derivative of any number 0? Because is there a variable here? No. So if it was, we would call it x to the what? If there's no variable, it's x to the, and what's anything times 0? Are we okay? So we now have this little extra shortcut here. So what if I put all of this together and let's give you an initial test and see what you can do. So what if I asked you for the derivative of x to the 10 minus 3x to the 5th plus 8x to the 1/4 minus 0.2x to the 0.3 minus 5x to the -3 plus 2/3 x minus 1,000. Give that a try. Give that a try. Give that a try. Notice I've given you 1, 2, 3, 4, 5, 6, 7 terms. Your job is just to find the derivative of each one. Find the derivative of each one. So if we have a bunch of terms all next to each other, we just take the derivative of each one. So this is going to be x to the 9. This is going to be minus 15x to the 4. This is going to be 1/4 times 8, which is 2. And if you're like, oh, I don't know what 1/4 minus 1 is, it's -3/4. And if you need help with that, you have a calculator. You shouldn't need help with that. But if you do, you can put in parenthesis 1/4, close parenthesis, minus 1. That gives you -0.75, which is totally fine. Or you can press math, number 1 for fraction, and it can change it to -3/4. So there are no excuses, right? No excuses. So that's that one. Same thing here. If you're not sure what 0.2 times 0.3 is, 0.2 times 0.3 is 0.06. Okay. So you get minus 0.06x subtract 1 should be negative 0.7. Again, if you need your calculator, use that. Negative times negative is positive, 15x to the negative 4. Again, reason it out, but that would be 2/3. And the derivative of negative 1,000, like the derivative of anything, is 0. Now, this is where we're going to get a little bit of an issue. I wouldn't leave that as a final answer. I believe you should always make negative exponents positive. Why? Real quick, just say it out loud. What is 3 squared? Real quick. 9. What's 3 to the negative 2? We're not sure, right? But if we rewrite it, it's clear that it's 1/9. So the deal is we prefer positive exponents to negative exponents. And the reason why I say that is what I would do is if I had negative exponents, I would get in the habit of rewriting them. And you'll see why a little bit later in the lesson. But this would be 10x to the 9 minus 15x to the 4 minus 2 over x to the 3/4 minus 0.06 x to the 0.7 plus 15 over x to the 4 plus 2/3. But then, inevitably, someone's going to say, but if I don't do it, do I get it wrong on the test? And then I get mad. Okay? I'm not going to get mad. But the deal is, just do it. It's simpler. It makes more sense. Now, would I take points off? Probably not, because it's the same thing. But trust me, if I do it, I have a reason. And you're going to find that reason out very soon, that if you have negative exponents, or sometimes it needs to be rewritten to make more sense. That concept is really important. Okay, so take a minute, make sure everything makes sense. Take a minute, make sure everything makes sense. We're going to start 2.5, but we're not going to get very much into it. Sorry, 2.5, because I've already really done most of 2.5, but I want to go over a few weird ones. And to me, they're not weird, but to you, they're going to be weird. Okay. So when we go to 2.5, just a little reminder, how do I show that it's a derivative? Well, you have that prime. That's to show it's a derivative. Another way to write it is dy over dx or d over dx. Those are some ways that you can show that's a derivative. That's a derivative. That's derivative notation. Now, we've already talked about these rules, but I want to bring it up. The derivative of any number is 0. Derivative of 1,000, 0. 2/3, 0. Negative a billion, 0. The derivative of any number is 0. We talked about that. Then let's do some weird ones. What do you think the derivative of 10 pi squared is? What is the derivative of 10 pi squared? And you're like, oh, we've never done pi. But what's the answer? What's the answer? 10 pi squared. Once I hear it, I'll tell you if you're right. What's the derivative of 10 pi squared? If you don't know what pi is, 3.14 blah, 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 you know, circumference of a circle, dealing with circles. Remember area of a circle, circumference of a circle, pi. Nope.
It's 10 pi squared.
Nope. Haven't heard the answer yet. Nope. 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 I just told you that pi is 3.1 da, da, da. Pi is just a number. Zero. What's the derivative of any number? 0. What is pi? A number. A number squared times a number all ends up being a number. And again, I've taught this. You know this, but see, these are the weird ones. Are we okay? So again, the derivative of any number is 0. So what's the derivative of negative 24? Derivative of 12? Negative square root of 7? 0. It's just a number. Negative pi. It's all 0. Are we okay? So again, it's just right now you need experience. You know what to do, but you need experience. And with experience, you'll get better. I've already taught you the basic rule. The basic rule is exponent goes to the front and subtract 1. Okay, that's just a rule written with notations. So what's the derivative of x to the fifth? 5x4. Okay, so again, the basics we got, you just need some experience. So let's give you some experience. Let's just do these four out loud. What's the derivative of x to the 6? 6x fifth. What's the derivative of x to the 30th? Right, no worries at all. What's the derivative of t raised to negative 2? Ooh, some of us are simplifying. Let's keep it simple. So negative 2 t to the negative 3. And yes, I would like it simplified like that. Okay. What about x to the 3 halves? 3 halves x 1/2. Good. You know your fractions. See how we kind of slow down a little bit, right? Know your fractions. Now, here's a weird one. My advice to you, I want the derivative of that. My advice to you is take the derivative of that, but it may need to be set up. It may need a little extra work before you can take the derivative. Don't say it out loud. Don't say it out loud. Give everybody a chance. Notice the way it's written is difficult to take the derivative. So do I have some knowledge of exponents? Can this be rewritten? And the answer is what? X to the negative 5. Isn't it exactly the same thing? Now that you rewrote it, what would be the derivative? Negative 5, x to the negative 6, which can be rewritten as negative 5x to the 6. Do you see that little trick of rewriting it? Do you see why I want you to learn how to rewrite it? It's going to help you when the problems get a little harder. Okay, so you may need to set it up first. For example, the next one. In case anybody needs the previous one. Take the derivative of 4th root of x to the 3rd. Can you take the derivative of it? Yes, you can, but you may need to set it up first. Again, sometimes you need to rewrite it first, which would be x to the 3/4, right? Then when you take the derivative, this would be 3/4 x to the negative 1/4, which could be rewritten as 3/4 x to the 1/4. Okay, so to end class today, I'm going to give you 3 problems to try. All 3 of them, you need to rewrite it first. You need to rewrite it first. So give these 3 a try. Be careful. A, B, and C. And yes, they all need to be rewritten first. So be careful. Be careful. Give all 3 of them a try. Okay, so we're going to find the derivative of all 3, but notice that all 3 need to be rewritten first. So I'm just going to do the rewriting part first. So for the first one, this is 1 over x, x to the 1. So when it goes up, that's going to be x to the negative 1. I'll take the derivative in just a little bit. And then the second one, that's going to be cube root of u squared. That's going to be u to the 2/3. And actually, we're doing u this time. It doesn't always have to be x. It could be any letter. Okay, and then here we have, again, we can call it x. This is 1 over square root of x. And if you're like square root of x, how can I rewrite that? X to the 1/2. And again, if you're like, I've never seen that. We went over that when we did exponents and logs. And I put a bunch of stars by it, reminding you that that's going to come back. And it's back. Okay, why? There's a 1 here and there's a 2 there. That's where the 1/2 comes from. But it needs to move up. So this becomes x to the negative 1/2. X to the negative 1/2. Please note that these are still the original. We've not taken the derivative yet. We've not taken the derivative yet. I've only rewritten them. Are we okay? Good so far? So now when we take the derivative, and sometimes people rewrite it and they're like, I'm done. You didn't take the derivative. All you've done is rewrite it. So this is going to be negative 1 x to the negative 2, which I would rewrite as a final answer, negative 1 over x squared. Again, why do I rewrite it? Because if I had to plug a number in, I'd rather plug it into a positive. The second one, if I took the derivative, would be 2/3 u to the -1/3. Again, if you need to use your calculator, do what you got to do. If you're getting them wrong, try to figure out what happened. Getting them wrong is no problem at all. Not fixing it is the problem, right? So if you're not getting these right, try to figure out what happened. Is it a fraction problem? Is it an algebra problem? Or is it actually the derivative problem? And then the last one, the -1/2 goes in front. Be careful, -1/2 minus 1 is -3/2, or you can put 1.5, that's fine. And I would write this as -1/2 x to the 3/2. So if you got them correct, fantastic. If you got them wrong, fantastic. Fix your mistake. Try to figure out what happened. But again, the lesson's the same. Exponent goes to the front, subtract 1. The issues we're having are not calculus. The issues we're having are algebra, fractions, decimals, square roots, not calculus, not calculus.